Anthony is, I think, quite distinguished in the Sydney data science community with a master's in analytics from Northwestern University in the United States, and prior to that, a background in the actuarial field. Anthony has a passion, a devotion, an obsession to analytics, data science, at all its aspects, however high and strategic or detailed and technical and everything in between. He's currently at CBIG, a data analytics consultancy, where he's, as I understand it, spearheading the data science function.
Yeah.
And apart from that, he has been an energetic, active contributor to the data science field here in Sydney. He runs a regular data science breakfast, and every time I catch up with him, he is just bursting with energy and thoughts and interest in the field. And I'm really looking forward to finding out about differential privacy, which is his topic today. Thank you, Anthony.
Thank you. Hello. Okay, thanks very much for such a great introduction. Bit of a disclaimer, I've spent most of today sitting in bed sick, so just bear with me and my croak, and don't ask too difficult questions. I'm quite ramped up on painkillers, so take it easy on me. All right, so I'm going to talk about differential privacy. Maybe just as a quick show of hands, who here has heard of differential privacy before? Great. Okay, perfect audience, because this is an introduction. So just quickly about me, as Eugene mentioned, I work as a decision scientist at CBIG Consulting. Not quite sure why they call it decision scientist. I think it's to keep the recruiters away, but anyway. So I also, as Eugene mentioned, I help run the data science breakfast meetup. So, rather than coming after work, I figured we'd have a breakfast instead. It's a much smaller group, very different to what goes on here, but usually quite a nice active discussion. So I know all of you are always welcome. So put that out there. And the other thing I'm doing at the moment, which I won't plug too much, but along with two others, I just started what's called the Minerva Collective. It's a not-for-profit that seeks to engage, to match the right analysts to the right data to the right social problems. So, it's kind of like a data science for social good, but also that, so we partner with Data Republic, so we can take advantage of some of the data that they have in that platform. So again, not going to talk about it too much today because we've just started and we don't really have any projects yet. Very, very early, but stay tuned. Anyway, I'm not going to talk about any of this today. I'm actually going to talk about some work that I did a couple years ago when I was interning in San Francisco at the company called Newstar. So I'd spent 3 months there, summer intern, while I was doing the Master of Science. And pretty much my whole gig, the main task was to write a blog post about differential privacy. So research it and then make it interesting. And so I did that. As I said, took the majority of that 3 months. It was obviously really interesting and great living in San Francisco, which is kind of like data science central when it comes to, just everything going on there. And my articles actually got quite a bit of airplay. So 100,000 views or something. I got cited in The Economist and Vice magazine, a few other magazines and things. So that was kind of cool. So, and also most importantly, it got a good reception from the privacy community. So there was some content to it as well. So the importance of privacy. Again, show of hands. Who's got an account at Google with Google? Okay. So we're all familiar with having a digital identity. Probably wouldn't be too thrilled if someone was to steal that, or to be able to view some of that information that you've got, like Hillary Clinton, for example. Also, so the Snowden movie. Has anyone seen the Snowden movie? So yeah, that's more about security, I'd say, but very much kind of shows the power and how scary it can be when privacy is compromised. Anyway, if you haven't seen it, I recommend it. It's very good. Anyone have an Ashley Madison account? No? Okay. I'll take your word for it. Okay, this talk isn't about that. Really, these are more, as I said, to do with security, as well as the law and even ethics and morality. It's a really big area. I'm not going to try to cover all of that. Yeah, sorry, Snowden. So rather, I'm going to focus on privacy in the context of data access, and in particular, open data and data sharing. But this does kind of go across a few fields. So yeah, I encourage you to be creative. So how is data privatized now, currently? There's a few different methods. So anonymization, which I'm sure all of you are familiar with. So if you want to share data that potentially has personally identifiable information, you're probably going to either get rid of those fields or, you know, do a hash function or something on it so that it's a unique identifier, but the data's not actually there. You can't get any value out of it. There are other methods, so k-anonymity, L-diversity. I'm sure there's a slew of other methods. I'm not a privacy expert. Probably should have done that disclaimer at first as well. But, you know, there are other methods. But what's worth saying is that all of these have been shown to be vulnerable to attack. So an example is there was a Massachusetts governor, I think, who had his health information released. So they managed to match his birth date and zip code and stuff like that, and were able to match that to data in the health database, and were able to show that it was his. I mean, there's millions of attacks like this, but what was interesting about that one is someone did a study on that and then worked out that about 63% of the population of the US can be uniquely identified by just their birth date, their gender, and their zip code. So yeah, I think originally it was like 84%, and then they did a better study and came with 63. So, you know, it's a bit scary, but so anonymization isn't really enough, particularly if it's not done properly. So what differential privacy guarantees is, so it operates off a solid mathematical foundation, making it possible to provide strong theoretical guarantees on the privacy and utility of released data. So I'll go into how that works. So, starting with an example. Say you have access to a database that allows you to compute the total income of all residents in a certain area. So just imagine Sydney, say. Everyone who lives in Sydney, you've got that number. So if you knew that Mrs. Dubosarski was going to move to another area, simply querying this database before and after the move would allow you to deduce his income, right? So there he drives off. So here's the formal definition. I'll go back to the example, but yeah. So okay, I think I had a question there, but anyway. So a random function k gives epsilon differential privacy if for all data sets d and d dash differing on at most one row and all s part of range k. Okay, probability that k of d is an element of s is less than or equal to e to the epsilon. Probability k d dash is an element of s. So in English, the risk to one's privacy should not substantially, as bounded by epsilon, increase as a result of participating in a statistical database. So that's where the differential comes from. It's talking about the difference of having one individual. So what this means is an attacker should not be able to learn any information about any participant that they could not learn if the participant opted out of the database. So there should be no risk to you for being part of a database, or if you weren't part of it, in terms of your own privacy being compromised. So that's the theory. That is what we're trying to get to. The way to do that is to add noise to the results. So we pretty much, I mean, there's a few different ways in which this can be done, and it's called a mechanism, so the function k. But, you know, you don't have to think too hard to consider if you take a number and you add a statistical distribution to it, so it's a random variable, you're going to get a different number, and that's going to be random. So the one that's commonly used is the Laplace mechanism. Unfortunately, that went off the edge, but just imagine a normal distribution with a point in the middle. So that's what the Laplace distribution looks like. So it's symmetrical, and it's yeah. So how much noise do we add? So it depends on epsilon, as well as the risk to the most different individual. So let's just think back to our example. So Eugene's moved out of the area. So if we were to add the noise to the result of that query before and after he moved, then we're going to get different results every time we run that query. So if we were to bound it like this, so I'm not going to go fully through all the formulas, but the most different individual, that would be the person, if you got total income, you'd take the person with the most income. They're the most different individual. They're the person who are most at risk of being, having their privacy violated. So you define that as the sensitivity, which in this case would be, say, $1 million. And then, you add a Laplace random variable, which is the sensitivity over epsilon to the query. So just out of interest, hopefully you can all follow me. Can anyone potentially see an issue with this? Yep.
If you know what that distribution is, you can back it up.
Well, it's a random variable, so potentially, but you're kind of close.
Makes your data less accurate?
Well, yeah, but you've got to have a trade-off between accuracy and privacy.
Could you query it like a billion times?
Thank you. Perfect. Exactly. Unfortunately, it might have been a bit obvious if you could see the whole distribution. But it's a symmetrical distribution. If you queried it 1 million times, you're going to end up with the mean, which is going to be 0. So you end up with the same answer. So the way that this is counted in practice is with what's called a privacy budget. So you take this epsilon, which is a small number, and then for each query session, and it depends on the implementation, but for each session, you're going to have a set of epsilons that you can get to. So you can set your budget for each query, but you're only allowed to do a certain amount of epsilon. A certain amount of privacy is released for every query session. Now, it can get quite complicated, so I'm just going to leave it at that. But that kind of answers that question. So if I go back to our example, so total income before the move, say we had for Sydney $50 million. After the move, $49 million, so that means that Eugene earns $1 million. If we privatize it, so this is just using an epsilon of 0.5, then it kind of gives these different results. And when you subtract the two, you end up with 8 million. But this changes every time because it's a random variable. So if we just start building a histogram, these numbers change every time. So you can't ever work it out from any individual query. Obviously, if you make this go, have a really high privacy budget, then if you have a look, you'll see that the income here, sorry, I need to get my mouse over to the side. So the income here is a bit closer to that million. So you just see it's, sorry, it's only working on my screen. I was wondering why that wasn't working. Sorry, so if I step through here, this is with this particular privacy budget. If we have a higher budget, then our numbers are closer to the $1 million. But as we back it out, so if we were to be able to run millions of queries, then you can see it starts to conform to a Laplace distribution. So it centers around $1 million. Okay. So in the context of this blog post, I thought, well, okay, that's the basics of differential privacy. There's obviously a bit more to it, but that's kind of the high-level overview. What I thought I'd do then is something a bit more sensational, which was actually show how privacy can be violated for a fairly standard data set that had been released, that probably shouldn't have been released, and then show how differential privacy can be applied. So I'll quickly walk you through that. So a lot of you might be familiar with this data set, New York City taxis. It's a data set that had all taxi rides, so the yellow cabs in New York in 2013. So that includes drop-off coordinates, right down to the, really small area, many decimal places, pickup coordinates, the amount of the fare, the amount of the tip, the number of passengers. I think there was a bit more. And what was actually interesting about it, why it first hit the headlines, was because it had these hashed license and medallion numbers. So when it was released, it had these kind of two variables that were PII, they'd been hashed, but a clever hacker just went in and said, oh, I kind of recognize that one value. This is just MD5, and just reversed it because he had a list of all the license plates. So everyone was like up in arms, and they thought, this is really bad. Now we can identify taxis and all that, which, is fair enough. But I actually thought that's not the real risk with this data set. It actually has another really big risk, which is the privacy risk to passengers. So I'm going to show you how a few passengers' privacy got violated by me. And yeah, you can make your own judgments as to how. So sorry, it's see if I can zoom out. Okay, well anyway, this guy on the left is Bradley Cooper. That's Jessica Alba. I spent some really fun few hours kind of going through Google Images and looking for pictures of celebrities with cabs in New York in 2013, finding the number, finding them in the database, and then tracking their trip. So yeah, I was that guy. But you can see, you can see the trips that they took. I mean, I did this in 2014, so, there's no real risk with this, but I was making a point. So what actually was really interesting about this was when I published this, I started getting all these emails from gossip magazines. And what they really picked up on was I said, by the way, I found these trips, but I also found out how much they tipped. And it was 0. So they were like, these celebrities, they don't tip their cabbies. Never mind the fact that I think like 99.9% of cash trips in New York, the tip isn't recorded for obvious reasons. So, the cabbies just take the cash and don't record the tip, obviously. So anyway, they paid in cash and they got lit up because of it. And I think Jessica Alba's agent might have, but she was contacted. She didn't contact me, but anyway, it's kind of funny. But this is a bit more of a kind of worrying visualization that I've got here. So somewhere over here, maybe I'll use the mouse so these guys can see. So this is where Larry Flint's Hustler Club is. So somewhere in Hell's Kitchen in New York. And I just tracked trips that had been picked up between like 2 and 6 in the morning every night, and looked at where they'd been dropped off. And then I kind of clustered those. The yellow dots are where there's kind of a lot of points in one area. Did a few things just to filter out all the Manhattan locations so that you could really track it to people's houses. And yeah, you can kind of see who's been visiting Hustler. So yeah, everyone's really happy that's out. So I mean, just out of interest, I tried a couple of those yellow dots and just looked at the address, saw if I could find any information on like who lived there or anything like that, and it wasn't that hard. Like you can pretty easily find out who those people are. So not a good thing. So how do we apply differential privacy? So yeah, hopefully that kind of raises a few questions, but let's think about how we could take that same data set and apply differential privacy to insulate those individuals. So again, we want to add noise. Now it's a bit different here because this is a map. So if you jump on the blog, actually I've got the SQL query that just pulls out those particular trips. But as you can see from the map, they're point queries. So, it's specific points. It's like going, how many taxis picked up a passenger outside a certain place at like 7:35 on July 8th, which, comes back with a pretty specific response. You can't just add noise to that because, if there's any, that's already telling you something. So what you have to do is you have to kind of aggregate it. So differential privacy works on aggregations. So this is what I call a histogram approach. So we drop a grid over the map, and then we just do the counts in each cell. And based on those, we can privatize the map. So if I just jump to this link, whoop, wrong page. Here we go. So this is for Jessica Alba. So the original trip, I think, dropped her off over here. So this is the actual data, but with privacy applied. And I did it to the tips as well. But you can, this is what the map would look like. So if you just imagine those red squares, it's pretty random. You have no idea really where she got dropped off. And even if, you look at a few different queries, there's very little to find. Now, again, if you had a much higher budget, then you can see, okay, these squares are really filled. There's another one in here because there was another taxi ride at that exact time. So that wasn't her. But you have a question?
But there are some squares there with or grid cells which are predominantly over the river.
Yeah, so look, my application of this was like, I'm just going to drop a grid on the map and count everything. Now, we know for a fact that there are no rides in any of these areas.
Some at the back where you have just a small portion of land.
Sorry, what was
Like that one back.
I can't go back.
Yeah.
It's random.
But you only have a small section of the square.
Yeah.
And the rest of it's in water.
Yeah, so look, if I was a proper cartographer, I'd go into the detail of actually trying to split up Manhattan into proper areas. And particularly in some areas where there's a lot of, like around here, where there's a lot of congestion, you might have smaller grid squares and things like that. But the point of this is really to show that you have no idea. You're trying to find one taxi ride and this is giving you nothing. If I were to look at, how do I get back? This one, which is the the Hustler Club. I think it takes a bit longer to load, if it loads at all. Yeah, so now there's a lot more trips in here. As you saw from that map, there are a lot of points there. So there's some utility in it. You're getting an idea of where these people live, somewhat. But again, you can't go down to someone's house. And yes, you could make the grid finer, but then it's just going to make it's going to make them more sparse, really, because a lot of them will be zero, and you just be adding on this high random variable every time. All right. Other queries. So again, those of you who are familiar with this data set, it's not just about identifying people on maps. I wanted to show how you could apply differential privacy to other types of queries, some that were of interest to some other academics and things. So this is just a graph of average speed. So we're looking at, this is for all drivers, I believe, and we privatize it here. So as you can see, we're looking at 100,000 drivers or 1 million. I can't remember exactly what it is, but there's a lot of drivers here, and applying differential privacy has no effect on the result. Again, this is at quite a kind of strict privacy level, and if you look at the top graph, it's barely moving. So this is showing the average speed at each hour of the day, but this is for one driver over the year, and as you can see, it's kind of nonsensical. So again, it applies, to protect the individual, but you can still get the aggregate statistics out of it. I've got another one here which shows driver income. So looking at this, the bars, so I think the yellow bars are just the actual revenue within the year. The pink bars are the privatized revenue. Again, shows very little link. But this is the average for all drivers. And again, at strict privacy, you're not seeing much difference at all. So you're getting the right information that you need out of it without compromising any individual. Going back to a map query, this is for all pickup locations, I believe. The dots are the actual pickups and the squares are the privatized pickups. You're not seeing much difference for everyone, but for an individual driver, kind of, he hangs around there, but you couldn't tell from the map. Okay. So it was just a kind of quick demonstration of differential privacy and what it looks like when it's applied. Again, as queries become more complex, it becomes more complex to apply differential privacy, but it's actively being worked on. So just in conclusion, I just kind of put forward some thoughts that I think are worth thinking about. So within the context of this, as well as the context of any open data that's released. So what should have been released by the New York City Taxi and Limousine Commission? Probably not as it was. I shouldn't be able to identify who went to Hustler. or the celebrities for that matter. I think the example I had, which I kind of got browbeaten a bit by a privacy researcher, he looked at it and I said, look, you know, potentially a wife could kind of see her husband coming back on a cab and then find out where he came from and all that. He was like, you're just scaring people. But, you know, I think it's a worthwhile point. How should the public be able to access it? So how do we kind of work with these privacy budgets and query sessions and things like that? Is it in line with the law? And if not, how should the law be changed to accommodate private data release? So with this in mind, I mean, most privacy laws and litigation is around kind of anonymization and strict kind of data sharing procedures and PII and all that. And I'm not an expert at that, but I know this isn't being done. So I feel like there are certain breaches that are possible of data that's been released with the best of intentions. So just to conclude, as data scientists, it's in our best interest to encourage free data flow in our society and lead the charge to ensure participants in these data sets are protected. The science is clearly there and will continue to be developed in the coming years. The onus is now on industry and governments to pay attention and embrace differential privacy to protect their stakeholders and citizens. Questions?
All right, well, please first of all join me in thanking Anthony. Time being what it is, we have time for 2 questions and relatively quick ones, and then we'll have a bit of networking time when people can ask Anthony more questions, or Jordan for that matter. So, first question. It's always the same guys.
Front and center.
Hi, thanks for the talk. I was just going to ask, there's a few things. What's the performance hit when you're applying differential privacy on average, I would say? And then a second sort of question is, you mentioned that if you hit enough, well, simulations or tries at it,
Yeah.
that you can sort of figure out how much it's adjusting on average to work out individual cases. Do you think that that's possible to gain with enough compute power, or is it something where it's a bit restricted, you need smart thinking to get at it?
I'd say it's neither. It's more like a rule that kind of, so I guess let me first answer your first question, which was how can you kind of control the accuracy, which was around really this, sorry, I don't have it up here, but that slider, that epsilon budget. So it's an active area of research is the kind of short answer. How to set these privacy budgets is something there's no kind of average, there's no known kind of even a rule of thumb or anything as far as I'm aware. But I think it becomes one sets up the data and sets up the kinds of queries that could be asked of it, and then you tune the privacy budget to a level at which one can kind of assure that there's no privacy being released, or at least an acceptable amount. And then in terms of the frequent queries, well, I guess one has to look at that and then say, okay, we have, if you run this query 10 times, then that's a problem. So we cap it at 5, something like that. Yeah.
I just wanted to say, does that have a performance hit for machine learning algorithms? Because Apple's...
It's actually fairly simple. I mean, so I don't know that much about differentially private machine learning. I know that's also being worked on. But really, you're just adding a random variable to the answer, so it's really quick to compute. Yeah.
So, last question, please.
Interesting talk. I've never heard of differential privacy before today. But
Well done.
I was just wondering, how much does it depend on anticipating the queries that people are going to make?
Yeah, quite largely. So this is part of why it's been so difficult to apply in practice. Now, I mean, I mentioned Data Republic before because we're doing this data sharing initiative with them. And one of the first questions I asked them, they're very much centered around, well, how can we assure privacy in these data sharing arrangements? And I said, well, how about differential privacy? Another one is the New South Wales Data Analytics Centre. They're also dealing with highly sensitive data. They want to get it out to analysts and things like that. It sometimes doesn't cut it to just remove PII. So, yeah, I mean, it kind of needs to be done if people can use this for research, but it's difficult. So I believe Data 61 are working on something at the moment that will allow this to kind of become productionized. But I mean, I last looked at this a couple of years ago, so I kind of follow it, but I don't, I'm not involved. Yeah.
All right, can you please join me once again in thanking you?